In this video, we are going to talk about the mean value theorem, which you should be familiar with from first year calculus. But if you don't remember it, don't worry because we will definitely cover it. First, we will look at Rolle's theorem, which is used to prove the mean value theorem. And the value of the mean value theorem is that it is used to prove a number of theorems that you are familiar with and used constantly in first year calculus. Theorems such as if a function has a min or maximum, then the derivative at that point is equal to 0. Or another theorem, if f of x, if the derivative is equal to 0 over an interval ab, that means f is constant on that interval. Also, if two functions have the same derivative, that means their functions differ only by a constant c. Another theorem that you're familiar with, again, that is proven using the mean value theorem is if the derivative is greater than 0, then f is a strictly increasing function. If the derivative is less than 0, then f is strictly decreasing. We will also go over the intermediate value theorem for derivatives, which is related to the intermediate value theorem, and we will look at the inverse function theorem. We will start by proving the theorem that the derivative at a function's max or minimum is equal to 0. So if f is differentiable on an open interval ab, and if f assumes its min or maximum at a point c in ab, then f prime of c is equal to 0. We'll start by assuming that f is at its maximum at c, that is, f of x is less than f of c for all x on the open interval ab. We are going to let xn be a sequence that converges to c such that xn is greater than a and less than c for all n. And since a is less than c, we may, for example, take xn equal to c minus 1 over n for some n sufficiently large. Then, since f is differentiable, and that's given as one of our hypotheses in our theorem, so f is differentiable at c, then the sequence f of x of n minus f of c over xn minus c converges to f prime of c using the theorem from our last video that says f is differentiable at c if and only if every sequence xn that converges to c implies that the sequence f of xn minus f of c over xn minus c also converges. And remember, this is our formula for the derivative. But each term in this series of quotients, and quotients, there are these quotients, the f of xn minus f of c over xn minus c. This series is non-negative, and it's non-negative because f of xn is less than f of c, and we know that because, remember, f of c is where f is at its maximum, so this top part is positive. Also, we chose xn to be less than c. In other words, it's a sequence that approaches c from the left-hand side. So since xn is less than c, this part of the quotient is also positive, so this whole quotient is non-negative for each term. Thus, we are going to have f prime of c is greater than 0, and this comes from the corollary. If tn converges to t, in this case, our sequence tn is this sequence here of the quotients, and it converges to t, that is, it converges to f of c, and all of our tn, these quotients, are greater than 0, so that must mean t, which is our derivative, our f of c, is also greater than 0. We can do something similar with yn. This is a sequence converging to c, but in this case, it's converging to c from the right. In other words, yn is greater than c and less than b, right? Just compare that to here. So now we're converging to c from the right. The terms in these sequence are all non-positive for similar reasons, and the sequence of quotient again converges to f prime of c. Now what we have is our sequence when we approach c from the left, that f prime of c is greater than or equal to 0. When we approach with a sequence from the right, when we approach c from the right, we get f prime of c is less than or equal to 0. So these two results both need to be true, which implies that f prime of c must equal 0. Hence, we've proved this theorem that when f assumes its min or max at a point c, then the derivative at c is equal to 0, which you know from first year calculus. But now you should know how to prove that. Also in beginning calculus, to look for a min or max on a closed function ab, a closed interval ab, we need to consider 1, the point x where f prime of x is equal to 0, and 2, we also have to check the endpoints, and 3, we need to check the points where f is not differentiable. And when you think about it, all 3 cases make sense that you would need to check for min or max, except it's really easy to forget number 2 to check the endpoints and number 3 where f is not differentiable. Next, we will look at Rolle's theorem that says if f is a continuous function on a closed interval a, b, which is why I have the endpoints dotted, that is differentiable on the open interval a, b such that f of a is equal to f of b, so here I have f of a is equal to f of b, then there exists at least one point c on the open interval such that the derivative of f at c is equal to 0. In other words, the slope of the tangent at this point is equal to 0. So here I have a point C, where the slope is equal to 0, and actually in this drawing I have another point where f prime of C, or f prime of whatever this point is equal to 0. And now we need to be able to prove Rolle's theorem. Since f is continuous and also continuous on this closed set, which means it contains its endpoint and therefore is compact, then from this corollary here, which says that if we have a compact set and f is continuous on that compact set, then f assumes min and max values on D. That is, there's x1 where f of x1 is a minimum, so it's less than all values of f of x, and x2 is where f of x2 is a maximum. In other words, it's larger than all f of x. So since f is continuous and compact, then this corollary will tell us there exist points x1 and x2 such that f of x1 is a minimum and f of x2 is a maximum. If x1 and x2 are both endpoints, then this f of x1 becomes f of a is less than or equal to f of x, which is less than f of b, which implies that f of x equals f of a equals f of b. In this case, f is a constant function and the derivative is equal to 0, which is what we wanted to show. Otherwise, f assumes either a max or min at some point c in the interval, and by this theorem here about the derivative of min and max being equal to 0, that means at this point c, where there's either a min or max, f prime of c must equal to 0, which is also exactly what we wanted to show. In either case, we have shown there is a point c where f prime of c is equal to 0. Now we have proven Rolle's theorem, again that says if f is a continuous function on the closed interval ab and it's differentiable on the open interval, and if a and b, the endpoints, are equal, then there's at least one point c such that f prime of c is equal to 0. Now we can go on to the mean value theorem that says if f is a continuous function on the closed interval ab and it's differentiable on the open interval, then there exists at least one point c in ab such that the derivative of f at c is equal to f of b minus f of a over b minus a. Graphically, this f of b minus f of a over b minus a, this is just the slope between the points a and b. So here I have the point A and B, and I've drawn in the slope. And what we're saying is there's some other point C in the interval such that the derivative at C, the slope of the tangent at C, is equal to the slope between A and B. Before we get to the proof of the mean value theorem, I just want to compare these two theorems. They're both about f being continuous on the closed interval, and they're about being differentiable on the open interval. In Rolle's theorem, it's the special case when f of a equals f of b, in which case you know that there's a point c where the derivative is equal to 0. In other words, it has a min or max. Here, for the mean value theorem, a does not necessarily equal to b, in which case Rolle's theorem no longer applies. But what we do know is there is a point c that has the same slope as the slope between a and b. And here I have that written out. So if f of a does not equal to f of b, Rolle's theorem does not apply. But there exists a c on the open interval such that the tangent to the graph at x equals c will be parallel to the chord between the endpoints of the graph. For this theorem, we will be referring to this graph. Here I have f of x, our function graphed out, it's the curve, and then here I have the line between f of a and f of b graphed out, and I have the equation. So you can see the slope of the line is f of b minus f of a, that is the rise, over the run, b minus a. So this, I am going to call this g of x. And then one last thing I am going to define, which is h of x, and h of x is going to be the distance, the difference between f of x and g of x, the difference between the function and this line here between f of a and f of b. And to do this proof, we are going to use Rolle's theorem. But of course, you should be saying we can't use Rolle's theorem because f of a does not equal to f of b. They are clearly different, and this is clearly a condition of Rolle's theorem. But we're going to do something very clever, or we're going to feel very clever, even if we didn't originally think about it, but at least we can understand this. We are going to use Rolle's theorem on h of x because, as you can see, at the endpoints, h of x is equal to 0. There's no distance between f and g. And also at this endpoint here, h of x is equal to 0. So now we can apply Rolle's theorem to h of x. And to apply Rolle's theorem, we can see that h is continuous, and also it's differentiable on the open interval. And what we know is since h of a is equal to h of b, which both endpoints is equal to 0, now we have that h satisfies the condition of Rolle's theorem, and there exists a point, by Rolle's theorem, there exists a point c in AB such that h prime of c is equal to 0. But now we have 0 is equal to h prime of c, which is equal to f minus g. Remember, f is our function, minus g, that's our line, so that's how we defined h, which is equal to, we have f prime of c, and the derivative of this function here is just the slope, which is f of b minus f of a over b minus a. And with just a little bit of algebra, we can get f prime of c is equal to f of b minus f of a divided by b minus a, which is exactly what we wanted to prove. Now we have the mean value theorem, so even when f of a does not equal to f of b, what we can say is there's a point such that the derivative at this point c, the slope of the tangent line, is equal to the slope of the line between a and b. For our first example of the mean value theorem, we are going to derive Bernoulli's inequality, which I have written out here for you. So 1 plus x to the n is greater than or equal to 1 plus n times x for all n natural numbers and all x greater than 0. I'm going to start with this equation here, and I'm going to define f of t equals 1 plus t to the n on the interval 0 to x. So you may notice I switched my variable to t because I wanted my interval to be in terms of x, my variable. So by the mean value theorem, there exists a c in this interval 0 to x such that f prime of c is equal to f of x minus f of 0 all over x minus 0. And remember, in this case, our x is going to be our rightmost endpoint, or b, plays the role of b, and 0 is our leftmost endpoint, playing the role of a in our mean value theorem. So manipulating this algebraically, we get f of x minus f of 0 is equal to f of c times x minus 0. If we look at our derivative of f, the derivative of f is going to be n, 1 plus t to the n minus 1. And so when I look at the derivative of f at c, we are going to have n, 1 plus c, all to the n minus 1. So this is our derivative, f of c. So now, looking at this equation, my f of x, I have 1 plus x to the n minus f of 0. So when I plug in 0 here, I'm just going to get 1. And that's going to equal to f of c, which I have written here, n, 1 plus c to the n minus 1, times x minus 0, which is just equal to x. And now, because 1 plus c is greater than 1, we can see that this product here is greater than n times x. Pulling my 1 plus x to the n minus 1 down here, it's greater than or equal to n times x, pulling that from over here, and then with some algebra you can see that I get exactly what I wanted to prove. For our next example, we are going to estimate the value of 40, the square root of 40, by using the fact that it is close to the square root of 36, which we know to be 6. And we are going to use the mean value theorem to f of x is equal to the square root of x on the closed interval 36 to 40. We note that the derivative of f is equal to square root of x, 1/2 x to the minus 1/2. So by the mean value theorem, f prime of c, which is equal to 1/2 c to the minus 1/2, is equal to f of b. In this case, b is equal to 40, minus f of a is equal to 36, all over b minus a. And some algebra will get us to this line here. Because c is in the interval between 36 and 40, we know c is in between 36 and 40. Taking the square root of everything, we have 6 is less than square root of c, which is less than square root of 40, and the square root of 40 is less than 7, which is just, I chose 7 because it's 1 greater than 6. So taking the reciprocal of everything, we have that 1 over the square root of c is bound between 1/7 and 1/6. And now I'm really close. I have my 40 minus 6 here is equal to 2 times 1 over c. So I'm going to substitute my 1/7 times 2 over here, and my 2 times 1/6 over here. And then adding 6 to both sides, I get the bound for square root of 40 is between 6 and 2/7 and 6 and 1/3. Our next theorem is f is continuous and differentiable. If the derivative of f of x is equal to 0 for all x, then f is constant on the interval. And we are going to do this proof by contradiction. We are going to suppose that f is not constant on the interval, and then we will use the mean value theorem to come up with a contradiction. If x is not constant, that means we have x1 and x2 such that one of them is bigger than the other, and they may or may not be equal to the endpoints. And we also know that f of x1 is not equal to f of x2. But by the mean value theorem, that means f prime of c is equal to f of x2 minus f of x1 over x2 minus x1. But since f of x1 is not equal to f of x2, this denominator over here is not equal to 0, meaning the derivative is not equal to 0, leading to a contradiction. And we can conclude f is constant. And from this theorem, we can prove this corollary. If f and g are continuous on the closed interval ab and differentiable on the open interval ab, if f prime of x is equal to g prime of x for all x in ab, then there exists a constant c such that f is equal to g plus c. And the proof follows directly from this previous theorem, and you apply it to f minus g. And this corollary should be very familiar to you because remember in first year calculus when you did integration, you would integrate and then you'd get a family of functions that all had the same derivative except that they might vary by a constant c. So that's why after you integrated, you always added a constant c, which is exactly what this corollary is about. If you have two functions that have equal derivatives, then the functions are equal up to a term of a constant c. We also have this theorem, if f is differentiable on an interval I, then f prime of x, the derivative greater than 0, meaning its change is in the positive direction, that means it's strictly increasing on the interval. If f prime is less than 0, meaning its change is negative, that means f is strictly decreasing on the interval. This is another theorem that's familiar to you from first year calculus, but in this class we're going to learn how to prove this theorem using the mean value theorem. We're going to start by supposing the derivative is positive, and we have x1 and x2 in our interval with x1 less than x2. Since f is differentiable and continuous, then we can use the mean value theorem, and that implies that there exists a c in our interval x1, x2 such that f prime of c is equal to f of x2 minus f of x1 all over x2 minus x1. Since f prime of c is greater than 0 because f of x is greater than 0 for all x, and also x2 minus x1 is greater than 0 because x1 is less than x2, that must mean everything here is greater than 0. That must mean f of x2 minus f of x1 must be greater than 0, which is exactly what we need to show that f is increasing. And the proof for part B is similar. And now we have our intermediate value theorem for derivatives. Let f be differentiable on AB and suppose k is a number between f prime of A and f prime of B. Then there must exist a point C in the interval such that f prime of C is equal to k. The best way to get an intuitive understanding of the intermediate value theorem for derivatives is to look at the intermediate value theorem, like the plain intermediate value theorem from first-year calculus, which says if f is continuous on an interval and k is a number between f of A and f of B, there must exist a point C in AB such that f of C is equal to k. So here I have my function f on the interval A to B, and it is continuous, as you can see. And then there's this number k here that's between f of A and f of B. So any number between f of A and f of B, there must be some value c that maps to f of k. Without this intermediate value property, that would mean we could find some k, let's say k prime, in between f of A and f of B that is not defined by f of k. There's no value here that maps to f of k prime, which would mean this function is not continuous. It either has a hole or a jump or some sort of discontinuity. So what this intermediate value theorem for derivatives is saying is that derivatives has this intermediate value property, that to go from one derivative to the next, you're not going to be skipping or jumping around or jumping over some value. We are going to start this proof by assuming f prime of A is less than f prime of B, and then k is a number between these two. So we have f prime of A is less than k, which is less than f prime of B. For x in this interval, we're going to define a new function g, and we're going to define it to be equal to f of x minus kx. So g is differentiable since f is differentiable and k times x is differentiable. And g prime of A, so g prime is going to be f prime of A minus, and the derivative of this will just be k, which since f prime of A is less than k is going to be less than 0, which is less than g prime of B. Because g is differentiable, that must mean g is continuous on the compact set AB, and it's compact because it contains its endpoints. So a continuous function on a compact set will assume minimum and maximum values on the interval, and our claim is C, we're going to look at the minimum, is in the open interval AB. Before we get bogged down into proving that C, which is the minimum of AB, is in the open interval, I want to say that if f is a minimum, then that means g prime of C is equal to 0 by our theorem here that says when f assumes it's min or max, then the derivative is equal to C. So g prime of C is equal to 0, and to remind you, g of x is equal to f of x minus k of x, so g prime of x is equal to f prime of x minus k. So plugging in C, we get f prime of C minus k, and since this is equal to 0, we will have shown that f prime of C is equal to k, which is exactly what we want to show. But one last detail, which is to show that C is actually in the open interval. To show that C is not equal to B, we can consider g prime of B, which we know is greater than 0, and is also, so it's greater than 0, and is also equal to the limit as x approaches b of g of x minus g of b all over x minus b. So this ratio here we know is greater than 0, or it's positive. But we also need to consider that x does not equal to b. So we're looking at some neighborhood u with the deleted point b, a deleted neighborhood of b intersected with ab. So this ratio is positive. Thus, for x less than b, and again, remember because x is in the interval and b is at the end, so x less than b with x in u, in this deleted neighborhood of b, we have g of x minus g of x is less than g of b. Hence, g of b is not the minimum of g on AB, so C is not equal to B. A similar argument can show that C does not equal to A. So what we conclude is C in the interval AB, and it's a minimum of G. So G prime of C is equal to 0 because of this theorem here, that if f has a min or max, then its derivative at that point is 0. So G prime of C is equal to 0. And looking at our definition of G, G prime is also equal to f prime of x minus k. So G prime of C is also equal to f prime of C minus k. Since that's equal to 0, that implies that f prime of C is equal to k, which is exactly what we wanted to show. The last theorem is the inverse function theorem, which says if f is differentiable on an interval I and f prime of x is not equal to 0 for any x and I, then f is injective and f inverse is differentiable on f of I. And f inverse prime at y is equal to 1 over f prime of x, where y equals f of x. And I rewrote the formula by hand here because I didn't like the way it looked when I was doing it on my computer, since these, I don't know, it just looks sloppy to me. So here it is, I rewrote this formula. I'm not going to prove this theorem, but I will give you a little bit of a picture to show you what's going on and then do a couple of examples. And the idea is if you have two functions that are inverses of each other, for example, the exponential function and the logarithmic function, when you graph them, they should be reflections across the y equals x line. So when you're looking at different tangent lines, you can see that there's going to be this relationship. And in fact, this right here is what gives us the relationship. Our first example is let n be a natural number and let y equal f of x equal x to the 1 over n for x greater than 0. Then f is the inverse of the function g of y, which is equal to y to the n. Use the inverse function theorem to verify the derivative of the formula f prime of x is equal to 1 over n, x raised to the 1 over n minus 1. I started by writing my function, so f of x is equal to x 1 over n, and that maps to some value y. And then my inverse function can take my value of y and then map that to y to the n, and that will be what gives it the inverse. I also take my inverse function and I take the derivative of it. So f inverse prime of y is equal to n times y n minus 1. And I want to use this now to find the derivative of f of x, or f prime of x. My theorem gives me a formula for the derivative of the inverse, but I want the derivative of the function f. So I just kind of took this formula here, and I just rewrote it. So I have my f prime of x is equal to 1 over f inverse prime of y. And I'm almost ready to plug in. But one thing is, because this is f prime of x and my variables are x, I should really rewrite this y so it's in terms of x. And I have that formula right here, which is f of x. So my f prime of x is going to be 1 over f inverse prime of x to the 1 over n. And now I can plug this value of y into my derivative, which is right here. So that's going to be 1 over, and now I'm going to have n times my value of y, which is x to the 1 over n, raised to the n minus 1. And the rest is just algebra to get it back into this form that we wanted to show. For our next example, we are going to look at f of x is equal to x squared plus 1, and g of x is equal to x minus 1 raised to the 1/2. And it turns out we're going to graph these. You can see they're reflected across, well, if I did a good job graphing, they're reflected across the x-axis, and you can verify f of x and g of x are inverses. And I rewrote my g of x as the inverse of f because I like to be able to plug it into this formula directly. So if I look at what I have f of x is equal to x squared plus 1, and that gives me a value of y. When I plug in this value y into my inverse, which is y minus 1 to the 1/2, I'll get back my x. And then also I can take the derivative of my inverse, so f inverse prime of y is equal to taking the derivative 1/2 y minus 1 to the minus 1/2. Plugging directly into this formula, I can find f inverse prime at 5 is equal to 1/2 5 minus 1, which is 4, raised to the minus 1/2, which is just equal to 1/4. Now I can use the formula for my inverse function theorem that says f inverse prime of y is equal to 1 over f prime of x. So f inverse prime of 5. Now you have to remember that this is x and this is y. So you have to convert this y into an x. So you want to know what it is, what f of x maps to y equals 5. And we have that here, which was a note that f of 2 is equal to 5. So over here we want to put 1 over f prime of 2. And plugging into our formula for the derivative of f of x, that would be 2x. So our final answer is 1/4, which agrees with this answer here. Reviewing at what we've discussed in this video, first we looked at the theorem at the derivative of a function at its min and max point, and the derivative is equal to 0. We looked at Rolle's theorem that said on an interval between a and b, if it's continuous on the closed interval, differentiable on the open interval, and f of a is equal to f of b, then there's at least one point where the derivative is equal to 0. We looked at the mean value theorem. Again, if it's continuous on the closed interval, differentiable on the open interval, then there's at least one point such that the derivative at that one point, c, is equal to the slope of the line between a and b, the endpoints of the interval. We said if f was continuous and differentiable, then the derivative equals 0, means f is constant. We looked at, again, f differentiable. If the derivative is greater than 0, then it's increasing on the interval. If it's less than 0, then it's decreasing. We had this corollary here that said if the derivative of two functions were equal, that means the original functions differ only by a constant c. We looked at the intermediate value theorem for derivatives, which said that the derivatives had the intermediate value property, meaning that if f is differentiable and k is a number between f prime of a and f prime of b, then there exists a point c such that f prime of c is equal to k. In other words, the derivative doesn't jump around. If it goes from f of a to f of b, and there's some number in between f of a and f of b, there has to be a derivative in between as well. We looked at the inverse function theorem. So if f is differentiable, we can calculate the derivative of its inverse at a point without actually having to compute the derivative of the inverse. I have 4 problems now for you to try. On the next slide, I have a hint for problem number 4. And then the slide after that, I have solutions. So pause the videos and give the problems a try. Here is the hint for problem number 4. Here are solutions for the first 2 problems and solutions for the last 2 problems. And that is it for this video. Thank you for watching.